Hello there and welcome to A-Level Further Maths. Here we're looking at damped and forced harmonic motion, so we can answer questions from exercise 8c. So this is linked to the exercise 8b where we had a look at simple harmonic motion. If you haven't had a look at that video already, then go ahead before watching this one here. So, in the previous section, the problems you solved related to simple harmonic motion. So that's just with this equation here, the second derivative plus omega squared x equals 0. This is a second order differential equation with no dx by dt term in it. You saw that this was based on the trigonometric graphs, and however, in many cases, the simple harmonic motion will not continue indefinitely and experience a damping effect which slows it down. So under the previous model, there'd be no slowing down of the simple harmonic motion, it would just carry on forever. But in real life, that's unlikely to happen. For example, a swing is subject to air resistance, so each oscillation becomes smaller than the previous one. If you were just to start a swing off and measure its horizontal distance, then that would be simple harmonic motion, but it would slow down after a while due to air resistance. Okay, so let's see what happens when we include a dx by dt term in as well. We'll start by sorting out the dx by dt term first though. So what happens when it's just d squared x by dt squared plus x equals 0. So here omega equals 1. Let's have a look and remind ourselves what happens when we don't have a dx by dt term. Auxiliary equation, and then it's straight into a trigonometric function. So it's purely trigonometric, and it would be x equals cos t plus sine t, and it would just be a trigonometric wave the whole way through. Okay, so that shows that the bog standard simple harmonic motion will carry on forever. There will always be oscillations in your motion, but really that doesn't really happen. So let's include one dx by dt term inside our simple harmonic motion. That's going to relate to something to do with the speed of the particle. So write down the auxiliary equation again. It'll be m squared plus m plus 1 equals 0 this time, with roots of minus a half plus or minus root 3 over 2i. Now we have to choose the appropriate form for our answer to go in, so it would be the complex form up here, where p is going to be minus a half, and q is going to be plus or minus root 3 over 2. Okay, and it's going to look like this one this time. Okay, so let's have a look at what we've got here and why might it look like this one. So it's going to be wavy because there's a sine and cos inside your function here, but it's also going to be exponentially decreasing because there's a scale factor of e to the minus half t. Remember, e to the minus x will look like a downward sloping graph towards the asymptote, and in this case here it's just going to slowly but surely make its way down towards the x-axis because it's got that decreasing exponential function. So this part here will be a very small part eventually, and this part here would just be a part in between the oscillating period. Okay, so that's how this graph will look. It's because it's got this part here. It's gonna move down towards the x-axis and oscillate around the x-axis. Okay, what happens if this time we're just going to put 2 dx by dt. Okay, so let's see what happens when this happens. So we'll write the auxiliary equation, solve for m. We get a repeated root this time. So what happens when we get a repeated root? It's this second form up here that we need to write our answer in. So it's going to be a plus bt and then e to the minus t. The root goes on the power of e there. So what will the graph of this thing look like? It will be a slowly decreasing graph down towards the x-axis. So it's not going to oscillate around the x-axis at all. It's just going to slowly go down to the x-axis. So that's for repeated roots. Let's now have a look at what will happen when we put 3 in the front of the dx by dt term there. Let's solve this equation here. So that's 2 different real roots, minus 3 plus or minus root 5 over 2. Let's put that into the exponential graph, exponential form of our second order differential equation answer, and it's going to get going to be very close to the x-axis very quickly, much more so than the previous one. The previous one just gently moved down towards the x-axis. This one here moved down towards the x-axis very quickly indeed. Okay, so we've had three different forms there. So the first one was just some simple harmonic motion, and that was just it's just gonna oscillate around the x-axis forever and ever. So that's simple harmonic motion. When we have complex roots, it's just gonna very lightly oscillate around the x-axis. It's going to be lightly damped. It's going to very slowly move its way down towards the x-axis so that it doesn't have any displacement anymore. The original roots were complex in this case, which effectively means that b squared minus 4ac is less than 0. When we had a repeated root, we had some critical damping. So what that meant was it slowly made its way down towards the x-axis. No oscillating there at all. These were repeated roots where b squared minus 4ac is equal to 0. And for the last one, where we had two real roots, we had heavy damping where it went down towards the x-axis very quickly. So therefore b squared minus 4ac is greater than 0. So the four different cases are on the page there for you now. So the first one is simple harmonic motion where we have no damping at all. This means that the simple harmonic motion is just going to happen forever and ever and ever and ever and ever and ever. In the second example, we have some damping, which means light damping, which means there will still be some oscillating, but the distance away from the origin will get smaller and smaller and smaller and smaller and smaller until it basically stops. In the third example here, we have a particle that will just tend towards the fixed position O again, so there'll be no oscillating there. It will just move back towards its original position very slowly. And in this one here, more like a door closing, it will just close very quickly, and there'll be no oscillating at all there. So the four different cases here. So the point to take from this is that a second order differential equation will lead to a different type of harmonic motion depending upon the numbers within the simple harmonic harmonic motion. Okay, so we always have a second derivative. We'll put k dx by dt, so it depends on what this value k is. If k squared is less than 4 omega squared, then that will mean that we have some light damping, some complex solutions. If k squared equals 4 omega squared, then that's going to mean critical damping, where it slowly goes down towards the x-axis. And if k squared is greater than 4 omega squared, then it would be heavy damping. Heavy damping and oscillations will not be performed. Okay, so it depends on your solutions to your second order differential equations. Complex will have some oscillations but a light damping. Repeated roots will have critical damping where it tends towards it very slowly. Heavy damping, when you've got real roots, will head towards your x-axis very quickly, so the distance from the origin will disappear very quickly indeed. All these rules come from b squared minus 4ac. Okay, so let's move on to an example then. So a particle P of mass 0.5 kilograms moves in a horizontal straight line. At time t seconds, the displacement of P from a fixed point O on the line is x meters, and the velocity of P is v meters per second. A force of magnitude 8x newtons acts on P in the direction PO. The particle is also subject to a resistance of magnitude 4v newtons. When t equals 0, x equals 1.5, and P is moving in the direction of x increasing with speed 4 meters per second. And the question here asks us to show that this second order differential equation looks like this. dx, second order differential plus 8dx by dt plus 16x equals 0. So remember that although x and v are not forces, there are forces in the question which are based on them. So let's draw a diagram and include all this on a picture then. So we'll mark a fixed point O and particle P. The distance from O to P will be given as x. So if we read through the question on the line, x meters and velocity v, so it's x meters away from the fixed origin O. A force of magnitude 8x newtons, so we're going to set We're going to set the acceleration going to the right, so rightwards will be positive here, but we'll show that that should be actually be negative in a second. So force of magnitude 8x newtons acts on P in the direction PO, so P to O, so that means that 8x magnitude will be acting to the left. And also the particle is also subject to a resistance of magnitude 4v. So when it says resistance, that means if it needs to be pulled back towards O in the opposite direction to the displacement that it already has. So it's pointing backwards on the 4v as well. When t equals 0, so now we've got all of our forces on the diagram. So what we need to do now is we now need to set up a little F equals ma equation. So what are our forces? We have two forces at the moment. There is a minus 4v force and a minus 8x force. The particle has a mass of 0.5 kilograms, so 0.5 will pop in there. And then we have the derivative, so we have the acceleration, which is acting to the right-hand direction. But you can see when we work out to the acceleration, it's equal to something negative on the left-hand side, so it is actually negative, but it's just standard notation to be pointing it in the positive direction, and then we just set it equal to something negative. Okay, so let's now rearrange and double both sides. So we've now got everything on the same side, so we've now got everything on the same positive side. Let's now rewrite these v and accelerations as differentials. So there we are, that's exactly what we need to show in part A. The second derivative plus 8 dx by dt plus 16x equals 0, and it all started from an F equals ma equation. So make sure you're good at doing those, because they're pretty tricky, those ones. You can still, however, move on to part B if you struggle with that little bit there. But make sure you can do that, because that's worth quite a few marks there. As long as you've got a diagram with some forces in the appropriate direction, always setting acceleration to be positive, then you're all good to go. But you will have a lot of negative forces involved. Okay, so find the value of x when t equals 1. So what they're asking us to do now is solve the differential equation. So we have a repeated root in this one, m equals minus 4. So it's going to be of this form here. That's what the second order differential equation answer form is when you have a repeated root. So now we need to use the information we have in A and to find A and B. So when t equals 0, x equals 1.5. and is moving in the direction of x increasing with speed 4. So that would be positive 4 rather than x decreasing, which would mean a velocity of minus 4. So let's put in t equals 0, x equals 1.5 to start with, and that will give us 1.5 equals a. We can go ahead and plug in what a is and then start differentiating. So we've differentiated from lines 1, 2, 3 and 4 here. Now we can plug in t equals 0 and v equals 4 because we have a speed of 4 where x is increasing. So plug in 4 for v and t equals 0, and we work out there that 4 equals minus 6 plus b. So therefore b must equal 10. So the final answer, well actually no, not the final answer, we now have the relationship for x in terms of t. It's 1.5 plus 10t e to the minus 4t. So now we can find the value of x when t equals 1. Let's go ahead and substitute that in, and we get this expression here. And if we calculate that, it will be 0.211 to 3 significant figures. That's in meters. Okay, so let's have a go at a second example now. So a particle P hangs freely in equilibrium attached to one end of a light elastic string. The other end of the string is attached to a fixed point A. The particle is pulled down and held at rest in a container of liquid which exerts a resistance on the motion P. P is then released from rest. While the string remains taut and the particle is in the liquid, the motion could be modelled using the equation of this expression down here, where k is a real positive constant. So the question is, find the general solution to the differential equation and state the type of damping the particle is subject to. So this is our second order differential equation. Let's solve it, find the general solution, and then decide what type of damping it's going to have. So auxiliary equation, factorize. Oh, this one nicely factorizes, that's good. So that's going to have two real solutions. So it's going to be the first type of solution to a second order differential equation where we have two distinct real roots. So that's going to involve very heavy damping because we have two real roots, so it's subject to heavy damping. So there we are, that's all they were looking for in this question here. Let's move on to a third example. One end of a light elastic spring is attached to a fixed point A. Particle P is attached to the other end and hangs in equilibrium vertically below A. A particle is pulled vertically down and its equilibrium position is released from rest. A resistance proportional to the speed of P acts on P. The equation of the motion of P is given as follows, and it's this expression here, where K is a positive real constant and X is the displacement of P from its equilibrium position. So part A is find the general solution to the differential equation. So let's go ahead and do that then. So write down the auxiliary equation. And this one doesn't factorize, so we'll have to get out our quadratic formula. And our quadratic formula tells us that we get solutions of minus k plus or minus ki. Okay, so we're going to have some imaginary, so complex roots here, so we're going to need the complex form of the answer. So that's going to be x equals e to the minus kt, so that's the real part coming in on the power, and then it's a cos, and then k, this k here will pop inside the cos and the sine. So it's a cos kt plus b sine kt. So that's the answer to the general form. So that's the answer to part A. Moving on to part B then, find the period of the motion. So the period of the motion is always 2 pi divided by omega. Omega here is k, so it's going to be 2 pi over k seconds. Okay then, so we've seen damped harmonic motion. Let's now have a look at forced harmonic motion involving situations when an outside force affects the motion. For example, when someone pushes a swing, it means the swing will oscillate differently to what it would do naturally. So second order non-homogeneous differential equations can be used to model this. Homogeneous just means it equals 0 on the right hand side. This is non-homogeneous, so it's not equal to just 0 on the right hand side. It looks like this thing here where we've got the second order differential equation and then equals some function of t on the right hand side. So f of t can be used to include the outside force, and you will therefore need to use particular integrals when solving these problems, just like we did a couple of sections ago. Okay, let's have a look at an example then. So a particle P of mass 1.5 kilograms is moving along the x-axis. At time t, the displacement of P from the origin O is x meters and the speed of P is v meters per second. 3 forces act on P, namely the restoring force of 7.5x, a resistance to motion of P of magnitude 6v, and a force of magnitude 12 sine t newtons acting in the direction OP. When t equals 0, x equals 5, and dx by dt equals 2. So the question is, show that this differential equation is what we're going to be working with here. So let's have a look at the words that are coming out of this example. We have a restoring force, and what a restoring force is, in which it acts to bring the particle into equilibrium or back to the origin O. So in this case, it acts in the direction PO. Okay, so let's draw a diagram and include the forces. So we have fixed point O and particle P. Acceleration will always be acting to the right. We have a restoring force and a resistance to motion force, so both of these will be acting to the left, where we're setting the acceleration to the right. We always set acceleration to the right when we set up our diagram like this, and yes, it will be mostly negatives that in this equation, but the 12 sine t force acting in the direction OP, O to P, so it's acting in the right hand direction. Okay, so let's now set up our equation using F equals ma. So F equals ma, so all the forces will go on the left, and then it will equal mass times acceleration. So we're setting rightwards as positive here, so it's going to be It's 12 sine t minus 6v minus 7.5x. So that's 12 sine t moving to the right. And then these two forces that are going leftward are in the negative direction if we resolve right to be horizontal. And then it equals mass times acceleration, 1.5 times x double dot. In this, when you set up a model like this, acceleration is always to the right. Let's now just do a bit of rearranging, so bring the negatives onto the positive side and divide through by 1.5, and we're going to get x double dot plus 4v plus 5x. That's very similar to what we've got here. All we need to do now is replace x double dot and v with the differential notation, so it's then going to be exactly what we have on the show that. Okay, there we are. So it's really important you can do these, taking a context question, setting it, putting it into a diagram, and then doing F equals ma on it. It gives you a good 4 or 5 marks there. Okay, let's move on to part B now. Find x as a function of t. So now first we've got to go through that whole process. Complementary function first. So let's solve it. We get an imaginary root, so we get complex root, so p equals minus 2 and q equals 1. So let's put that into the form of the answer. E to the minus 2t, a cos t plus b sin t. Now we'll work on the particular integral. So since the function involves sin t, we should consider using x equals p sin t plus q cos t as a possible form. Yes, it's got cos t and sin t in the complementary function, but that's being multiplied by e to the minus 2t, so we don't need to worry about multiplying by an extra t here. Okay, so let's take x equals p sin t plus q cos t. We'll differentiate it once, and we'll differentiate it again, and then we'll put all of those forms into the second order derivative. So let's substitute all of those in. It's going to be a big long equation. The second derivative will go first, plus 4 times the first derivative, plus 5 times the original x function. So that's where that goes. X dx by dt comes in, and then the x function comes in as well. We want 5 times that. Okay, let's expand the brackets and factorize. So we get 4p minus 4q sine t plus 4p plus 4q cos t equals 8 sine t. So let's now set up those simultaneous equations. The coefficient on sine is 4p minus 4q, which will equal 8 on the right hand side, and 4p plus 4q will equal 0 because there's no coses on the right hand side. Okay, let's now solve these simultaneous equations, and we get p equals 1, q equals minus 1. So we know what the particular integral is going to look like then. It's going to be x equals sine t minus cos t. And what we do is we go back to our original suggestion and put p and q in. So it's sine t minus cos t. So that's our particular integral. So the final answer then to this find x as a function of t is this big long expression here. It's e to the minus 2t brackets a cos t plus b sin t, close brackets, plus sin t minus cos t. Lovely, good stuff. And find x as a function of t. Right, so now what we can probably do is we can use this last bit of information from the example, which is t equals 0, x equals 5, dx by dt equals 2. So let's substitute those in. T equals 0, x equals 5 to start with, and that helps us work out that a will equal 6. So let's now rewrite out the expression with a equals 6 in it. Okay, so a has now been replaced with 6. And let's now differentiate again to put dx by dt in, which is 2. Okay, so we need a bit more space for this. So this is our function at the moment. So let's now differentiate using the product rule, and this is what we get here. So this term here will differentiate to this term here. We've shown it in derivative notation so far. So we're going to differentiate the back bit first and keep the front bit the same, and then we'll differentiate this bit here and keep the back bit the same, and then we've already differentiated this back bit here. So let's go ahead and calculate those derivatives, and that's what we get when we differentiate. Now we need to plug in the derivative of that is that. Lovely, good stuff. So now we need to put in t equals 0, dx by dt equals 2. So let's now work out what that needs to be. Cancel out lots of different parts there, where sine of 0 can just cancel out. And we get b to be 13. So we now have the full relationship. The full answer to this question here is x equals e to the minus 2t, bracket 6 cos t plus 13t, plus sine t minus cos t. And there we are, that's the answer to that example there. Okay, and then there's a part C, describe the motion when t is large. Okay, well when t is large, let's look at our equation and think about what might happen. We've got two kind of parts to this solution here. We've got a part that's being multiplied by e to the minus 2t, and we've got part of it that isn't being multiplied by e to the minus 2t. Now when x is large, e to the minus of a large number will just fizzle out to be 0. So this part of the curve here will just fizzle out to be 0. So when t is large, these two things at the back here are still going to oscillate. They're still going to go through the motion of 2 pi radians. Every 2 pi radians it will oscillate once. So when t is large, this bit here will just tend towards 0. So it's just x equals sine t minus cos t. So write x as a single trig function. So let's just write that as r sine t minus alpha, so that we can explain a bit more about what's happening when t is large. Okay, and we get the relationship being x equals root 2 times sine t minus pi by 4. So when t is large, this is another way of representing this function here. So what we can say then is that once we've turned it into this form, we've got a bit more information about what it's going to do as it oscillates. So it's going to oscillate every 2 pi seconds with an amplitude of root 2. Okay, the scale factor at the front of the sine gives us our amplitude. So it's going to be as t tends towards infinity, the motion becomes simple harmonic motion with amplitude root 2 and period 2 pi. Okay, so there we are. That's how we explain what happens when t is large. And if you're interested, this is what the graph will look like. So it will be exponential. There'll be a large exponential effect around this point here. And then as t gets bigger, it just turns into a sine and a cos wave. Okay, so let's do one final example then. A particle P is attached to end A of a light elastic string AB. Initially, the particle and the string lie at rest on a smooth horizontal plane. At time t equals 0, the end B of the string is set into motion and moves at a constant speed u in the direction AB. And the extension in the string is x. Air resistance acting on P is proportional to its speed. The subsequent motion can be modelled by the differential equation. This second order derivative here equals 2ku. Find an expression for x in terms of u, k and t. So before we start answering the question, what is going on here? So let's just imagine there is someone with now a piece of string attached to particle P. This particle here is particle P. And then the person starts walking to the right. Let's just say the particle starts walking to the right. What's going to happen is, because this string here is an elastic string, the initial movement by the person to the right will actually just stretch the string. And then as the person keeps on walking, what will happen then is the string will then start moving towards the person, because it will want to contract its elastic, and then it will once it's done that, it will then relax a bit more, and then stretch a bit more, and then contract a bit more, and then relax a bit more, and then contract a bit more, and then relax a bit more, and then contract a bit more. And it just keeps on going through that kind of oscillating process. So imagine you start walking in the box with constant speed. As the tension increases, the box will start to move towards you. However, as the tension decreases, as well as friction and air resistance coming into play, the box will then slow down again. So as it contracts, it will build up some extra speed compared to the person, but then as it contracts, the elastic kind of energy will diffuse, will reduce, and then it will slow down again. We end up with a movement that keeps the box moving, but with a variable speed. This is essentially what is happening in this question. the extension of the string will keep increasing and decreasing, which is what we're modeling here. So it's not just going to move in a steady line behind the person who is now walking to the right. It's going to move a little bit faster than the person, then a little bit slower than the person, a little bit faster than the person, a little bit slower than the person, a little bit faster than the person, a little bit slower than the person, because of this elastic property of the string. Okay, so let's start getting involved with this second order differential equation here. So this is the second order differential equation. Let's go to the auxiliary equation and then factorize it. So we're going to get a repeated root of m equals minus k. So the answer to that is now going to be x equals a plus bt e to the minus kt. Hopefully we're getting familiar with these three different forms of our answers now. Okay, so that's the complementary function. Now let's look at the particular integral. The particular integral here is just going to be a constant. Since the right hand side of the equation is a constant, we're just going to use x equals a as a possible form. Differentiate it once, differentiate it again, and we get 0 and 0. So we're just going to substitute a into the left hand side where x is, and then set it equal to the right hand side. So put a in and we get k squared a equals 2ku. Let's now just divide by k squared and we get a equals 2u over k. So that's the particular integral. The particular integral is 2u over k. So it's that part there. So the final expression for x in terms of u, k and t is going to be the complementary function plus the particular integral. So there we are. That's the answer for this question here. We also know that when t equals 0, the extension of the string is 0. So let's put t equals 0 and x equals 0. So the distance travelled is 0. It starts from the origin. And we could work out that a is minus 2u over k. And we also know that it starts from speed 0 as well. So put a back into the relationship and we can now differentiate it. And we'll then differentiate it using lots of product rules, and that's what we get when we differentiate it. Now we can plug in t equals 0, v equals u. Oh, v equals u. Time t equals 0, spring is set into motion and moves with constant speed u. Yes, lovely, there we are. So it tells us there in the question that t equals 0 is set into motion with speed u. So substitute u into the differential and t equals 0. And we get u equals 2u plus b, so b must therefore be minus u. So substitute that into the initial equation, and we get this expression here. So a has been substituted with minus 2u over k, and b has been substituted with minus u. Okay, and there we are. That's the answer to that part of the question there. That's all the examples we're going to go through. Loads, big video this one. So make sure if you're stuck at any parts, go back, have a little rewatch of it. Don't worry if you're rewatching it a couple of times, making notes as you go along, really highlighting, emphasizing key points that I've made throughout, and we'll now have a go at an example. Okay, so this is the question we're going to have a go at now. Pause the video and give this one a go. Okay, so let's have a go at this question here then. So a particle P is moving in a straight line at time t seconds. The displacement of P from a fixed point O is x. The motion of the particle is modelled by a differential equation. When t equals 0, P is at rest at a point where x equals 1. Find x as a function of t. Okay, so let's get started then. So it's going to be auxiliary equation first. And then we need to solve auxiliary equation. It might be the case that we are too big on this one. Yeah, let's complete the square. And now let's move that number onto the other side. So we get minus 5. So it's going to be m equals minus 1 plus or minus root 5i. Okay, so x is a function of t. So the first bit, the complementary function, is going to be e to the minus t. And then it's going to be a cos root 5 t plus b sine root 5 t. Okay, and it equals 0 on the right hand side, so there's no particular integral for this question here. But we can now plug in t equals 0, p is at rest, and x equals 1. So let's plug that in then. So it's going to be, first of all, 1 equals e to the minus 0, that's just 1. So it's going to be brackets a, and t equals 0, so that will just be 1, and t equals 0 here, so that will eliminate. So a equals 1. Next thing we'll do then is we'll rewrite out our relationship with a equals 1 in there. So it's going to be cos root 5t plus I, sorry, no, not plus I sine, plus b sine root 5t. Okay, so now we need to differentiate. So we're going to differentiate using the product rule. So dx by dt equals minus e to the minus t, and then all of this stuff here. So I've differentiated the exponential first. Now I'll differentiate the thing at the back, so it's going to be e to the minus t brackets minus root 5 sine root 5t, and then it's going to be plus root 5b cos root 5t. Okay, let's now plug in t equals 0 and p equals 0 as well. So it's at rest, so that equals 0. So it's going to be minus cos 1, so that would be minus 1, and then it would be plus, that would be 0, plus root 5b. So b is therefore going to be root 5 over 5. So the relationship between x and t is going to be when x equals e to the minus t brackets cos root 5t, and then plus root 5 over 5 sine root 5t. And there we are, that's the answer to part A. So the smallest value of t is greater than 0, for which p is instantaneously at rest, is t. Find the value of t. So we need to find when this expression here will first be at rest, other than when it starts at rest. So what we need to do then is differentiate it once and then set that equal to 0. So let's just rewrite out what we had before. It was x equals e to the minus t bracket cos root 5t plus root 5 over 5 sine root 5t. Okay, so we'll now need to differentiate it. So differential is going to be minus e to the minus t, and then we'll keep all this stuff here the same. And now we will differentiate the second part, so it's going to be plus e to the minus t, and then it's going to be root 5 sine root 5t, a bit of a minus on that one, and then it would be plus, that would be root 5 coming out to the front, that would just cancel out, so it would be cos root 5t. Okay, so the next thing we need to do now is set this thing equal to 0. I'm just going to cancel out the e to the minus t's, because that's not going to affect when the thing equals 0, because that's always a positive value. So it's going to be, let's just expand all the brackets, minus cos root 5t plus, so it would be a minus still, because it's a minus at the front, so I need to factorize, let's expand that minus, so it's be root 5 over 5 sine root 5t, and then it would be plus minus root 5 sine root 5t plus cos root 5t equals 0. So I've got a minus cos root 5t and a plus cos root 5t at the back there, and then I've got these two bits here. So it's going to be when sine of root 5t equals 0, So that's first going to be root 5t equals 0 or pi. So it's going to be when t equals pi over root 5 seconds. And there we are, that's the answer to this question 3 here. So there we are. That's the answer to this one. So have a go at plenty of the questions from exercise 8C. Again, as I said before, if you need to go back at any point and re-watch parts of this video, then you're very welcome to do so. It's a challenging exercise, probably one of the most challenging exercises in A-level further math. So really spend a lot of time on it, really get to grips with it. Have a go at those wordy questions, don't be afraid of the wordy ones, yeah, ask your teacher for help if you need to. Lovely, thanks very much for watching. Hopefully you found this video helpful.